So welcome to our next talk about finding vulnerabilities in closed-source PHP applications. Our speaker is Stefan Esser, and I'm very, very glad that he made it to the Congress this year. It was not easy to get it to talk about this topic, but I hope you enjoy the next one. Just welcome Stefan Esser.
Thank you. Okay, so welcome to my talk, Vulnerability Discovery in Closed-Source PHP Application. And for those that don't know who I am, my name is Stefan Esser. I'm from Cologne in Germany, and I work for approximately 10 years in information security, and for 8 years I'm a PHP core developer. Last year I did the month of PHP bugs, where I disclosed every day of the month at least one security vulnerability in PHP itself. And I'm the author and maintainer of the Zuhu project, which is a security extension to PHP. And last but not least, I'm head of research and development of Sektion 1 GmbH, which is a German web application security company. So what is the talk about? I want to speak about PHP source code encryption, about how to recover bytecode from these encrypted PHP applications, how to visualize the bytecode, how to do vulnerability discovery within the bytecode, and finally I will also tell you that decompilation is possible. First, why do people encrypt their PHP application? The first thing is many enterprise companies want to protect their intellectual property, and therefore they don't want to give out source code even to their customers, and so they encrypt the PHP application in a way that you can't see the source code and you cannot make changes. The next thing is PHP source code encryption software is often used used by shareware authors. Shareware usually has some license system that needs to be protected so that you can't make your key file yourself. And then, like I said before, another reason to encrypt your source code is so that your customer cannot change the source code. Quite often when you have a large PHP application, you give it to the customer and they make custom changes, and then they call your support hotline and ask you about features you never implemented because they implemented them themselves. So the bugs are also their own. And last but not least, some companies encrypt their PHP applications because they want to hide their own intellectual property violations so that no one can see how and where they stole code. So why do I care? The problem is, last year a customer for the first time asked me to audit an encrypted PHP application. Basically it was one of these shareware applications. He bought it and wasn't so sure about the security, and he gave the software to us, and we had to audit it, and at least the core libraries of this shareware product were encrypted. So normally you have no chance to get the source code, and you cannot do your usual source code audits on it. The next problem with PHP encryption tools is there are no public unpacking tools. There are some Russian or Chinese unpackers for some of the cryptors, but first of all they cost money, and secondly usually the GUI is in Chinese or in Russian, and have fun using them. Why do we care? We care because all the standard white box auditing mechanisms we are using, like a source code audit or like trying to hook some function and fuzz the application, they don't work with these encrypted PHP applications. On the one hand, there is no source code, so we cannot do a source code audit on these applications. And on the other hand, when we try to hook some functions like the MySQL query function and try to fuzz the application, suddenly our hooks will not be called because the engine internally works different with these cryptors available, and so our hooks will never hook, and so we will not catch the fuzzed elements. And last but not least, if we find vulnerabilities in closed source PHP applications, first of all, not so many people can find these vulnerabilities, so you maybe have some real 0 days. And on the other hand, even if your bugs leak, only the vendor can fix it. So normally when you have a PHP application and it's open source, anyone who get to know the vulnerability can just change the source code and can fix the vulnerability. But with encrypted PHP applications, only the author or the vendor can change and fix the vulnerability. When I speak about PHP when I speak about encrypted PHP applications, I don't mean this like encryptions, like they just create some obfuscated PHP code and then they call the base64 decode function to decode some string and then they evaluate the string. This is nothing I'm speaking about, because this kind of protection can be easily defeated by just changing the PHP source code and hook the eval function, and you just output the parameter of the eval function instead of executing it, and then you get the original source code back. Maybe you need to step through several layers, but usually you get the original source code, and this is not really a protection. What I speak about is something that looks like this. Here you can see an example from a SendGuard encrypted file, and basically you see a PHP header, then some marker to give IDEs the chance to see that this is not a text file by just embedding some binary data in the beginning. And then you get a lot of nonsense PHP that does only print out a banner saying this one is an encrypted file, please download the loader there and there. And in the end, in the last 2 or 3 lines, you see binary garbage. And this binary garbage is actually the encrypted PHP source code. And you see there's no chance that you can get the original source code from that, and maybe you can try. But actually, this is encrypted bytecode, and there's no source code anymore. So, for more secure PHP encryption, this is usually implemented below the user space, because everything you do in user space can be hooked from within PHP, and you can just see what they are doing. So, PHP encryptions are usually implemented in a loadable extension, and you cannot run the PHP application without the loader extension. For example, with the SendGuard, this is the send optimizer. If your server doesn't have the send optimizer, you cannot run SendGuard encrypted files. And what SendGuard actually does is it takes the PHP code, compiles it, the resulting bytecode is encrypted with several layers, and so the source code is completely gone. You cannot recover the original source code from there. I have some pictures. So normally you have the PHP source code, which is green, and this gets passed to the send compile function. The send compile function will first tokenize it, then compile it, and the result is some kind of PHP bytecode, and this bytecode is then passed to the send execute function that executes the bytecode. So what happens when we load the SendGuard or the send optimizer? The send optimizer will, first of all, it will hook in between the PHP source code and the PHP compiler, and will replace the compiler with something that's called the Guardian compiler. And the Guardian compiler will first check before it compiles the code. It will first check if this is actually a SendGuard encrypted file, and if it's encrypted, then it will call its own routines. Otherwise, it will just pass the file to the original compiler. With old encryptors, this was everything that was done. So, the compiler on the one hand gives the original source code to the original compiler when it's not encrypted. But when it's encrypted, it just decrypts it and executes it. And with older encryptors, this execution was done by passing the decrypted bytecode directly to the PHP executor. And so with old cryptors, once you had hooked the execute function, you had the original bytecode and could work on the bytecode. With newer cryptors, the complete executor is replaced with something different. And so in this case, send optimizer executes this encrypted PHP and not the PHP engine. So there's some available PHP bytecode encryptors. These are only the three most known. This is first SendGuard from Send. Then there's the IonCube PHP encoder from IonCube, and Source Guardian from Source Guardian. And there are a lot of different cryptors, especially the people behind Source Guardian have a lot of white-labeled cryptors that are all more or less the same, but they sell them to different users to different prices with different names. So when you see one of those cryptors and you cannot really see who is behind it, then most probably it's one of the Source Guardian ones. They have a lot of strange companies in Eastern Europe, and every country has a different cryptor, and yeah, but most of them are developed by Source Guardian people. So PHP source code encryption usually exists on three levels. First, we have the simple encryption, which means the PHP bytecode is encrypted. Then the second level is some kind of obfuscation. So within the PHP bytecode, they obfuscate function and variable names. The bytecode itself is not obfuscated by the current cryptors, only the names. And last but not least, the newer cryptors have some protection. So like I already said, anti-hooking functionality so that you cannot simply fuzz the application. So far, I already spoke about PHP bytecode, but what actually is PHP bytecode? When PHP developers talk about PHP bytecode, they usually mean the opcode arrays. And opcode arrays are some internal structure within the Send engine, and they are the smallest compilation execution unit that exists. And within this structure, there is the function name this opcode array belongs to, there's the file name, and there's the line numbers this was compiled from. There's some type information like which kind of function, which kind of method this is a private, protected, or public one. And there are some other flags like if this is an internal function or a Userspace function. And of course there are also information and about the function parameters. So within the opcode array there's a table of allowed function parameters with their default values, with their type hints if there are any, and of course there's also the number of minimal needed parameters and the maximum number of parameters stored within the opcode array. And last but not least, there's of course the bytecode, which is stored in kind of op lines, which are the opcode lines, and I will come to that now. For every op line in the PHP bytecode stores exactly one comment. You have there the opcode, like in many other, if you know assembly language, you know that you have usually an opcode and some parameters, and in PHP bytecode it's the same. You have the opcode, there are about 150 different opcodes in PHP. They are all very high level, and then you have an optional result parameter, an operand, a result operand, and you have 1, 2, or 3 optional operands. Here on the slides you only see operand 1 and operand 2 because in the beginning there were only 2 operands, 1 and 2, but some of the opcodes require more operands and then they are stored in the extension value. And there are very few, like 3 or 4 opcodes that still need more operands, and then they take 2 opcode lines in the opcode array, but there are only, like you need it for each and some array dimensions. But normally you only have 1 opcode line per opcode. And one very nice thing that is often not removed by cryptors, by the decryptors, is there's also, for every opcode, there's a field that stores the exact PHP source code line number this opcode was compiled from. Sometimes it doesn't work. If you have a statement that spans across several lines, then it doesn't work. Then you have only the last line in this number. But usually it works. So you know this opcode is from line 5 in the PHP file, so then you can look in the source if you have the source code. So something to the about the operands. In PHP, which is very important, there are 5 different operand types. First there's the const operand type, which is for constant values, like never changing things in the source code, like a defined string, a defined number, or something else, or a defined array. So these cannot change. So if you see them somewhere in the bytecode, you know that this cannot be user input because it's always a constant. The next thing is there are so-called temporary variables. These are for storing intermediate results of multiplications, additions, concatenations, and all the intermediate variables used by the engine. Then you have an operand type which is called var. These are the variables. So these variables are like references to real PHP variables. So when you see this kind of operand used, it's usually the reference to a real PHP variable. With PHP 5.1, there was a new type introduced, which is the CV, the compiled variable type, and this is basically the same like the var type, with the difference that simple local variables in a scope, they usually don't need to be looked up every time you access them. And earlier PHP versions, when you accessed, for example, the very long variable name variable, then every time you access them, every time you add something to it, every time you use it, PHP needs to look up this very long name in the table. And to speed this up, there was introduced a new type of variable, which is the compiled variable. So now PHP knows this is like the variable with index 5. And so now when in the opcode there's only stored I'm a compiled variable with index 5. So PHP doesn't need to look up the very long name. It just needs to look up index 5 in its own table, and then it knows where the variable is. This resulted in a very huge speed up between PHP 5.0 and 5.1. And last but not least, sometimes operands are just unused, which doesn't mean they are really unused. They just mean they are not one of the 4 I just mentioned. They are just not defined by the 4 previous ones. So this is actually everything you need to know about PHP bytecode. And after the bytecode is compiled, it will get passed to the executor. And the executor is very different in different PHP versions. In PHP 4, it was like one very large function with a lot of cases of a switch statement. And so it was one very large function that contained all the engine in it. And then with PHP 5, it was introduced that every opcode got an own handler function. So the executor just loops through the oplines and calls the handler. With PHP 5.1, with the introduction of the CV variables, another speed up was introduced. So now we have not 1 but 25 opcode handlers per opcode. So that PHP knows there are 2 operands, and now it knows the first one is a CV, and the second one is like unused. So then it can calculate which of the 25 one it needs to call. And there's a speed up because now every opcode handler doesn't need to look up, is this a CV? Then I need to access the variable this way. If it's a var, I need to access this variable this way. So now it actually can access it directly in the correct way, and this results in another speed up. which is very helpful for unpacking PHP, but you will see this later. So I already said for every combination of operands there are 5 different, for every combination of the 5 operands there's one opcode handler. So let's get back to the encryption. When I started working on the PHP bytecode encryptors, I was like, I'm lazy, I don't want to do it individually for every crypto. I worked on runtime encryptions during the days of DOS and early Windows cryptors, and so I knew that every time you crack a crypto, you just start a cat and mouse game. The vendor will change a few bits and suddenly your unpacker doesn't work anymore and you have work again. So it's a very time-consuming thing, and I want to spend my time on other things. So I didn't want to do reverse engineering on every new version of SendGuard or IronCube, and so I searched for a generic way to remove the bytecode encryptors. And therefore I searched weaknesses within the current bytecode encryptors. Like I already said, in the older cryptors, you had it that you had the hook of the compile function, and this hook just decrypted all the bytecode and then gave it to the original execute function and executed the bytecode by PHP. The problem with that is, at this point, of course, the bytecode is completely decrypted, so you don't need to do anything anymore. You just hook the send execute function and you get the decrypted bytecode for free. So you can do anything you want on this bytecode after that. And the other thing is the older cryptors, because they do not replace the executor, they cannot use obfuscation. Because if they want to do obfuscation, they need to hook within the engine so that some of their tricks still work. And right now, they don't do this. Well, actually, it would be possible, but they don't do it. They just decrypt everything and are ready. The modern cryptors, on the other hand, are completely different. The modern cryptors, they first try to obfuscate everything, and then they replace the executor. The good thing is, when you have a PHP application, you often have a large part which is the core, and the vendor doesn't want you to look into it and to change it, and then you have a lot of modules on the outside. The problem is, when you have modules on the outside, they are source code, and it's impossible to have obfuscated core with plain text modules on the outside, because the modules on the outside need to communicate with the core. And so if you obfuscate the core, the modules cannot access the core anymore. And therefore, most of the PHP applications, they are not encrypted with obfuscation activated. So usually most of these applications are not obfuscated at all. And therefore, removing the bytecode encryption is very easy. And even if you cannot deobfuscate because it's obfuscated, the thing is, for security analysis, you don't want the original source code. You don't need all the fancy variable names. They might help you, but you don't need them to do security analysis. So most of the cases, you don't care. The other thing is, this is the biggest weakness of the current encryptors, is they are also very lazy people. So they just steal PHP source code. Well, they use it. It's not stolen because it's allowed by the license. But they just take the original executor, just copy it. They just change a few things, and they just use the original executor, which means it works exactly the same like the internal PHP executor. Which also means they have the same very large opcode table in memory with 25 handlers per opcode. And we will use that for the generic decryption. The idea I came up with to create a generic unpacker was very simple. The idea was, I know the encryptor tool, the optimizer, for example, or the IronCube loader is loaded in memory, so somewhere in memory there must be the opcode table. the handler table. And so the first thing I do in the decryptor is to search this handler table in memory. How I do this, I will tell later. And then I replace all the opcodes in there, which is 25 times 150. I replace them all with so-called recording handlers. And then I just execute the PHP file as normally, but it's nothing executed, it's just recorded. And after that, I repair the op array and dump the op array everywhere I need, or store them for further analysis, or just print out the disassembly, whatever I want to do. So how do I find the opcode table? It's very simple. First, I start at the address of the replacement send execute form function, because I know this is the function, this is the address within the code segment of the optimizer or the encube loader. I also know that the data segment is loaded directly after the code segment with these dynamic libraries, and so I can just start scanning from the code pointer downward in the memory, and or upward, depending on how you like it. And then I search for this structure in memory. And actually finding the structure in memory is very simple, because I know it's aligned in memory. That means the bytes before will always be null. So I search for a single null pointer and then for something else. And this something else is, I know that there are 25 opcode handlers per opcode. So the first opcode is knob opcode. And there are no different types to implement a knob opcode. So every one of these 25 opcode handlers is the same. So I just search for a null pointer followed by 25, the same pointer in the code segment, and then followed by something different, which is not the same pointer. And by using this simple heuristic, I never found a false positive, so I always found the real opcode handler in memory, and from that I can work further. So the next problem is to detect the end of the opcode table. I already told you I'm lazy, so I don't detect that. I just know that SendGuard just replaces 150 or 51 opcodes. So for SendGuard it's always 151. For encube it's like 255, and Source Guardian they don't need this. So for now I only have these two very hard cryptors like SendGuard and encube encoder, and so I only need two hard-coded values, and maybe when there are new cryptors that use this functionality, I will try and write an automatic detection. The next thing is I just back up the original table into some of my own memory, and then I replace it with recording handlers. And these recording handlers just record the decrypted operands. When the moment the opcode handler is called, it gets called with the decrypted operands by the cryptors. So I just record what I see. I see, oh, I was a recording handler for opcode 5, and this is operand 1, this is operand 2, and these are the other operands or special flags. And then I just continue with the next opcode line. And I repeat this through all op arrays, through all methods, to all functions, and I trigger the execution of every bit of PHP code I see in the encrypted file, and I just store the decrypted op arrays in some memory place, or later I dump it to the disk. And after I'm ready with that, I just restore the backup of the opcode handlers to from my own memory to the table. And when I'm lucky, I survived this whole process without a segmentation fault. Sometimes this results in a segmentation fault. I still don't know why. But usually it works when you have like 4,000 encrypted files, maybe 10 are crashing the interpreter. And so until now I didn't need to really find out why it sometimes crashes. After I have the decrypted opcode array, there's a problem, because some of these encryptors, they also optimize the bytecode. And when they optimize the bytecode, they sometimes insert their own defined opcode handlers. No, they introduce new own opcodes. Especially SendGuardian introduces some function caching that works similar to the compiled variables. It's I call it compiled functions. I don't know how it's called internally by Send, but it's actually the same like the compiled variables for function names. So they replace all the call function opcodes with call function by index, and so they just have a number, and then they look up the function pointer in some internal array. The problem is when you don't know about these opcodes, you can't do anything with the opcode array because all functions are gone. You only see some unknown opcode and you can't do anything with it. So you need a little bit of reverse engineering to understand the new introduced opcodes. Right now there are 3 or 4. 3 of them are totally useless. They are just they are never used. They are just some corner cases optimizations that are never used. The most important one is the call function by index one. And you need maybe half an hour to reverse engineer what this thing is actually doing. And after that you know it and you can implement it in your encryptor. You can even repair the bytecode array by just replacing this with the original call function opcode and just switching the operand, which is a number, to a string, so that it's directly a function name. And so you have restored an original PHP bytecode array. Yeah, like I already said, a generic unpacker can either choose to ignore these unknown opcodes and remove them, or try to replace it. The problem is when you remove it, you maybe lose the logic of the program because you lose all function calls. Future encryptors might change other bytecodes, and so you will even lose more. So normally you need to reverse engineer this one or these 2 opcodes and handle them in your decryptor. But for now it's very simple because IonCube and the people behind SendGuard, they know that you can bypass their products, and they don't care because they just tell their customers to use obfuscation, and then the customer says, I cannot use obfuscation, and then they say, it's your own problem if you don't use obfuscation. And so they just don't invest much time in it. So at this point, you have the decrypted bytecode and the repaired bytecode somewhere either in the memory or on the disk, and now you have the problem, yeah, this is some bytecode, but now how do I find vulnerabilities in it? And I will try to explain 4 different things you can do with the bytecodes. First of all, you need some kind of user space access to the bytecode, so that your scripts can access the bytecode and read it, parse it, and whatever you want to do with it. And then I will show you how to visualize and navigate within the bytecode. I will show some slide about bytecode decompilation and some automatic analysis you can do on the bytecode. First of all, like I said, you need some way to access the bytecode from within PHP. A PHP application cannot access the bytecode directly. This is different maybe in other languages, but in PHP there's no way to get to the bytecode from within PHP without using some internal memory corruption or some overflow. Within the PHP world, there are 2 extensions to PHP that give you access to the bytecode. The first one is the Vulkan logic disassembler by Derek Rittans, and it basically is a disassembler of normal bytecode. And if you patch it a bit, you can even get the original bytecode from SourceGuardian, because SourceGuardian has no execution hooks, so it just hooks the execute function and dumps the opcodes at the execution function, and so you have the decrypted bytecode and can see it and disassemble it. The problem is the disassembly doesn't help you because it's a text, and you would need to parse the text and then restore some internal structure for yourself so that you can work on it. So Sarah Golleman wrote some different PHP extension which is called passkit. In passkit, there's nothing else but provides a function that is called passkit compile file, and you just call it and it will give you back a PHP array that contains all the internal information I just showed you on the previous slide. It just gives you a PHP array which is an exact copy of the bytecode arrays in memory. So you can work on it. The problem with passkit is that, let's say in 50% of the cases it will segfault. In the other 50% of the cases you will end up with some of the bytes with the opcodes correctly decoded, and some of the opcodes are simply wrong decoded because Sarah doesn't work on it anymore, and a lot of the information is just copy and pasted, and so a lot of opcodes in passkit doesn't work. But you can use it to get a rough idea of what I'm speaking about. Because of the problems with passkit, I developed my own extension which is called bytedisk, or sometimes bytekit. It's similar to passkit. Actually, it gives you all the features of passkit, but it gives you more things. First of all, of course, it gives you the raw opcode access like passkit does, but then it gives you also already the disassembled opcode. So you don't need to write a disassembler, you just use bytedisk or bytekit, and you get the disassembled opcodes for free. And then, of course, you get a function class list, but this you can also restore from the other arrays. And last but not least, this is the most important thing, it will give you code flow information. You will get for every opcode an array that tells you which opcode lines will be executed afterwards, which will be executed before. And so if you want to create a code flow graph, you can do this with this information very easily. If you're now Googling for bytedisk or bytekit, you will not find it because it's not public yet. I will release it within January when I cleaned up the code. Right now it's not public. So what can you do with bytekit or bytedisk? The first thing I tried was, the thing is, I hate simple disassemblies, and reading PHP code in disassemblies is very tiring. And I also wanted to create nice call graphs and nice flow graphs. And so I was searching for a way to graphically represent the PHP disassembly. And most of you maybe know binnavi, and my first idea was to just write a PHP to SQL script that exports the PHP bytecode to binnavi. For those that don't know binnavi, binnavi is a very nice tool to do binary audits, and it will look like this. And this is actually a PHP function within binnavi. This one is taken from, no, this one is not taken from FluxBB. This one is a demo function, and if you can read the bytecode, you will see that there is a include vulnerability in line, here I can't read it, but if you see the second box from bottom, there's an include of a variable. And this one is actually a function parameter, so if you call the function with untrusted user input, it will include an arbitrary PHP file, and you can execute any code you want. I will come to this later. Another thing you can do in binnavi is to look at the call graph, and in the large window you see a very small part of the call graph of this FluxBB, which is a port of, a fork of PunBB. And in the upper left corner, you see the complete call graph, which is a little bit complicated. This is the strange circle thing with a lot of dark lines. In every line is a call. And so you see sometimes PHP applications have very complicated call graphs too. Yeah, but so much for the visualization. The next thing I worked on was PHP decompilation. And I heard before that there are some non-free PHP decompilers, but I never knew how complicated it would be to decompile PHP code. And there was nothing public, and I didn't know anything about PHP decompilation at all, or decompilation at all. So I was just searching the internet for papers and came up with this reverse compilation thesis of Cristiana Cifuentes, which is maybe the most, maybe the well-known paper about decompilation. It's quite old, but I just read it and realized that everything in there can be used for PHP bytecode, and you don't need much more than what is in this paper. So the implementation of a decompiler for PHP was very straightforward, and it mainly consists of graph structuring algorithms, and after you have structured the graph, the code flow graphs of the functions, you can create PHP code from there. To show you how this looks, is on the left side you have the code flow graph of some PHP function. You see there are different colors for different parts of the graph, and actually these different parts of the graph are graph intervals. And the idea is to use graph intervals to find loops and to find nested loops, and the way you do this is you first find the intervals of the graph, and then you collapse every interval to an own node. In G2 you see that every one of the 4 intervals of the first graph is collapsed into a single node, and the edges between the intervals are now the edges between the nodes of the second graph. And you do the same again. You end up with G3, and you do the same again, and you end up with G4. And this is very good because it's a single node, which means the graph is not irreducible. This means you can create a very good disassembly from it, decompilation of it. If you have 3 or more, if you cannot reduce more than 3, because they reference each other, so you cannot reduce them anymore, then you have a problem. This usually is when your language supports Goto. Once the language supports Goto, you cannot create a nice decompilation anymore, because then you need to insert Goto statements, and sometimes you cannot know if you need a Goto or if it's a normal while or loop or something else. With PHP 5.3 there will also be Goto in PHP, but the thing is you will still not end up with irreducible graphs, because the thing with Goto in PHP 5.3 is that you can only jump out of control structures. You cannot jump into control structures, and so you will not end up with irreducible graphs. The next thing, okay, now this means actually that you have detected 2 loops in the PHP function that are nested. So after detecting the loops, you want to detect all the if statements, and therefore you just look at every node that has 2 follow nodes, and then you try to detect if it's an if then or if then else. And you do that by just checking if you do that by checking if the follow node of one branch is actually the other node that was branched in the other way. If this is the case, then it's an if then. Otherwise, it's an if then else. And when you do that, you ignore all the loop heads and tails. So because they already belong to a different control structure, and you don't need them anymore. The last thing is that you detect compound conditionals, which requires PHP jump change elimination. Otherwise, the algorithm doesn't work. It's not so interesting, actually. I'm running out of time, so I will try to speed up. The thing with PHP bytecode decompilation is that it benefits very much from the fact that the send engine has very high-level opcodes, and there's a huge amount of send engine metadata that also needs to be present within the encrypted bytecode, so you can restore a lot of things. And decompilation usually completely recovers unobfuscated code, and there are just small problems with protected members and classes, so that you will end up with when you have a child class, you will sometimes end up with the same function in two classes when actually the function was inherited. But sometimes it's not possible to detect that it was inherited. Yeah, and obfuscated code is still easier to read than bytecode. And one place where I tried this was Kayako Live Response. This was one of the shareware products I was talking about. And with Kayako, it's a case that you have only two files within Kayako are encrypted, and the customer said, "Well, audit it anyway. It's just two functions. There will not be a security vulnerability in it." Actually, he was very wrong. There was a cross-site scripting vulnerability in it, and you see that which is marked red. It outputs the query string and a post variable called query string directly to the template, and usually this needs to be encoded for HTML. And it's not done here, and so it's an XNS vulnerability. And the nice thing about this, it's within the encrypted file, so even if you know about it, you cannot protect yourself against it, because you cannot change the source code. You need to contact Kayako, and if you are lucky, they will not sue you because you know about it. And so, because you normally don't, you are not allowed to decompile the source code in some countries, and so you cannot fix it. They can fix it maybe, and yeah. Yeah, you said I can decompile the code and patch it. Yeah, like I said, but actually this is illegal in many countries. You cannot just decompile the code, and if you can decompile the code, you of course can patch it. But this doesn't help the millions of users that you are using it, and you cannot fix it and just provide other users the fixed version. That's still this is even more illegal. I didn't understand his question.
Why can't you provide a binary diff that anyone can apply? Why is that illegal? When did you become a lawyer?
Well, you can try that, but the problem is if you the thing to get a binary patch, you would need to just buy the send guard and encrypt it again, and then you need to diff the files, and too much trouble. So maybe I can get to the last topic, which is automatic bytecode analysis. The thing is, manual bytecode analysis is very time-consuming, and only if you are very crazy you want to read PHP bytecode, and normally you want to automate this stuff, and therefore, you can try simple pattern scanning, like normally many people that do source code audits start with a grep. You can do the same on bytecode, but it will give you much more information. And you can also do static and dynamic data flow analysis. I will show you some examples about pattern scanning. A question you usually have is, how and where is user input handled in the application? It's a very complicated question, but this actually means in PHP, where is there a read, write, or is that access to the superglobals, which are get, post, cookie, request, file, server, and environment variables. At bytecode level, you can answer this question very easily. You just search for 3 different kinds of bytecode, bytecode opcodes, which are fetch R, fetch W, and fetch I. And when you find them, you just check the operand, and if it's a constant string and it's one of the superglobals, you know that there was a read, write, or is-set access on this thing. If you have source code, you can of course use grep for this, but then you will you have two problems. First, you will get all the accesses that are commented out, and secondly, you only get the information there is access, but you don't get the information that is read, write, or is set access. And most of the time, you only want to read access. Sometimes you also want to write access because you want to know if they change the arrays and try to sanitize them in some way, and so you know exactly where in the application they sanitized the input data. The next thing you can do with simple pattern scanning is to answer the question, what include or eval statements are really 100% secure? This is, of course, a question that will not help you in many ways, but at bytecode level, this only means you search for the include or eval bytecode, opcode, and you just check if the operand is a constant. When you have an include or an eval on a constant value, it can't be influenced by user input, and so these occurrence of includes or evals are always safe. Now you may maybe think this doesn't help you, but when you have a large PHP application and there are like 100,000 includes, then have fun grabbing through them and just look for yourself if it's actually a constant or not. And by just checking this simple thing, you can eliminate a lot of false positives. Yeah, but actually when you do want to understand more complicated things, you need data flow analysis. And I will just provide a very simple example of a backward data flow analysis that just searches for hotspots, which are dangerous send engine opcodes or functions, and then it traces backwards through the operands or parameters and checks if this is actually safe or could be safe or it's unsafe. For this, I have a very simple PHP function that consists of a simple if condition, and one time it includes a constant string and one time it includes a string that could be influenced by user input, depending on the input to the function. When you compile this, you will end up with this bytecode. When you look at the bytecode, you already see that the opcodes are obviously very, very high level, so actually you can recreate the source code from this in your head, if you're crazy. So, okay, let's start. I said we are searching for hotspots, so we search for the include or eval comment, and we find it here. What we do is we check the operand. The operand is a constant string, so we know this one is safe, we don't care. So the next thing is we search for the next hotspot, which is there. We have an include on the temporary variable 6, and now we need to scan backwards where this variable was written to. Because we have the code flow information, we know that there's only one possible place where we can go. This is the line before. And we see there's a write access to temporary variable 6, and it uses compiled variable 1 and concatenates a constant string. We know the constant string is safe, so we need to know if the compiled variable 1 also safe. So we are now searching for write access to a compiled variable 1. We go backward again, and we end up in an include statement that doesn't write to our variables, so we don't care. But now, due to the code flow information, we know there are two possible previous lines. So we first go to the right, and we see there's a write access to our to our compiled variable 1, and it writes a constant string in there. We know a constant string is safe, so we ignore it. We just cut the branch there and go to the other side. On the other side, we have a jump opcode. Jump code doesn't write anywhere, so we don't care. The next thing is an assign. We see there's a temporary variable 2 that is assigned to the compiled variable 1. So now we need to find out what is actually temporary variable 2. So again, we go one line backward, and we see there's an array dimension on array an array that is stored in temporary variable 1, and the key action, this is stored in temporary variable 2. So now we know we don't know what temporary variable 1 is, so we need to find out what this is. So we go backward again 1 line, and there we see that it's actually the get array. We know the get array is user input, we consider it unsafe, and so we know that there's one code path at least that results in an unsafe include, and we can terminate here and say this function is unsafe. It doesn't matter what parameters the function uses, they're always unsafe. Of course, you can continue this, and if there are more hotspots, but right now there's only one. No, there's no hotspot anymore, and you don't care. Of course, this is a very, very simple example. It gets far more complicated when you have function calls, because then you need to trace all the parameters of the functions and not only the result operand that gets written to. And you also have the problem that when you have function parameters that are passed by reference, that are also possibly write accesses to your variables. So you also need to check if one of the parameters is actually the thing you are searching for. Gesundheit. Yeah, and this all looks very, very complicated, but when I experimented around with this, I was first implementing only a very small subset of the opcodes. You can see all the opcodes below. These are very, very few ones, but they help you a lot to just eliminate a lot of false positives when you're searching for include or require or evil statements that are unsafe. So these are just the opcodes that push variables or values to the stack, to the function stack. These are the opcodes that call functions. This is the include or evil opcode. Of course, you need to know it when you want to search include statements. It's a concat operator, which is used to concatenate strings, and last but not least, it's the fetch constant opcode. Usually you see a lot of PHP scripts that use include constant concatenated with something else. And to understand that, you need to fetch constant opcode. And actually, I tried this very simple thing on one of the PHP include vulnerabilities posted to Milworm. And this example program had a very many includes and requires. And normally you would have to go through this manually. And I just tried my simple code that only understands these few opcodes. And it was able to find exactly what was reported in this Milworm exploit. So it was two cases where get was directly used in an include statement, and so I could reproduce exactly the thing reported to Milworm with this simple code. So if you are interested in this, next month you can download the Bytekit and you can play around with this. Any questions?
Yes. Hello?
Yeah, where?
There is an open source compiler called Roadsend. Actually, it's a different implementation of PHP. Do you know that? And do you know if these methods fit to this too?
I never looked at Roadsend because I don't know anyone who's actually using it to protect his PHP code. Most of the people are either using IronCube or SendGuardian. And in most cases, they actually have bought both products, and you can either download its IronCube encoded or SendGuard encoded. But Roadsend is not so used so much.